Hello, I'm Evan Krell, and this is a quick look at some of our recent work in using explainable AI techniques for models that use gridded spatial input data. As complex machine learning techniques are becoming widespread, there's interest in figuring out what a trained model has actually learned. This may be useful for verifying that the model is applying realistic strategies. In this example, a classifier was trained to differentiate between wolf and husky photos. But here is an example where a husky was classified as a wolf. The image next to it is an XAI result that shows only the pixels that were involved in the decision. Because so many wolves are photographed against snow, the model learned the poor strategy to only consider whether or not the image has snow. We have been investigating using XAI for geospatial data and have identified challenges. It's very easy to apply XAI techniques, but the results may give a very misleading interpretation of how the model works. Here, the model detects clouds in the satellite image. Every image pixel is considered one model input feature, so that a typical XAI method will explain each pixel. But consider the effect of modifying that one white pixel. Model output should not change, so the pixel is not considered influential. But by that logic, no pixel will be detected. But then how did the model find clouds if none of the cloud pixels influenced it? This is because each pixel lacks semantic meaning in isolation. Instead, we can explain image patches, that is, superpixels. But there is very little principled guidance on how to form the groups, and we demonstrate that the choice of grouping scheme can greatly impact the user's interpretation of the model. Our case study is based on FogNet, a 3D CNN for coastal fog prediction. The input is a raster with 384 channels divided into 5 groups of related variables. Some of these, for example G1, wind, are 3D profiles with altitude and time step bands, so there is extensive autocorrelation in the data. Here we show XAI results from permutation feature importance, applied at 3 levels of granularity. We treat each of the 5 groups as a feature, each channel, and lastly 8 by 8 superpixels within each channel. To compare, we sum them up visually, inspecting their agreement. When using whole groups, we see that G1 through G3 each contribute around 20% of the performance. But the importance scores drop when using channels and practically disappear with channel-wise superpixels. The key is to understand how exactly each method probes the model to understand what question they ask. The superpixel results tell us that G1 through G3 are not important for isolated regions. The discrepancy among these three suggests that the model learns large-scale profile features, and this makes sense for these groups. For example, G3 is the thermodynamic profile. Our manuscript describes strategies for interpreting XAI results based on these feature grouping schemes.